Welcome to MEI Numerical Methods Convergence. In this video we'll be carrying on looking at numerical integration. Now suppose that we've calculated some midpoint or some trapezium rule estimates, then we can use the result that we established in the previous video concerning the ratio of differences to do some extrapolation. And if we've worked out T8 and T16, for example, then we have this result here concerning the ratio of differences, and we can use this to, if we rearrange this, we can see that we've got an expression for T32 approximately, so that if we've got T8 and T16 we can actually come up with an approximate value for T32 without working out any more estimates. And also if we had estimates for T16 and T32 we could come up with a value for T64 in exactly the same way. So you might like to pause the video and have a go at using these two results for T32 and T64 and see if you can express T64 in terms of just T16 and T8. So we've got these two expressions for T32 and T64 to start with, and then the expression for T64 gives us that if we replace T32 with that expression and then T32 minus T16, we can obtain from that expression there, so that becomes a quarter times T16 minus T8, and so this gives us the expression for T64 in terms of T16 and T8. So notice the pattern here. We've got T32, we've got a quarter times T16 minus T8, and for T64 we've got that same term, and then we've got 1 over 4 squared times T16 minus T8. So we can do the same thing for T128, and we get an extra term there, and we can see that we've got a geometric series after the T16. So the first term of our geometric series is a quarter T16 minus T8, and the common ratio is a quarter. So that gives us this expression, which we can call T infinity, which is our extrapolated figure, and that simplifies down to that expression, and that's if we had T8 and T16 calculated. If we'd had T16 and T32 calculated, for example, we could have done exactly the same thing and come up with that alternative expression for T infinity. Obviously it's going to be more accurate if you've got higher estimates such as T32 rather than T16, and then we can do exactly the same thing for the midpoint rule. So writing out the result again for T infinity, we've got that in terms of T16 and T8, and we can do the same sort of thing for Simpson's rule, again using for example S16 and S8, but now the constant of proportionality is a 16th instead of a quarter, and so that leads to a 15th instead of a third in the extrapolated expression. And once again, if we'd had S16 and S32 calculated, then it would be preferable to use them rather than S8 and S16. So that concludes this video, and we'll be looking at numerical differentiation in the next video.